człowieka, druga żena.
Microphone, thank you very much. Can you please take your seats? We're going to start in about 20 seconds. Right, so let's make a start if we can. So I'm pleased to see quite a lot of you here. I didn't go to the wine and cheese last night, but I know when you all came back. So some of you obviously were I think the party continued down by the lake by the sound of things, but it's good to see so many of you here for this plenary session. So we've got a session now on precision livestock farming. That's what PLF stands for. I think we assume everyone knows that, but maybe not everyone does. So this is using technology to monitor animals in terms of monitoring their health and their welfare and improving their management. And we're going to be focusing on measuring welfare and behaviour in this session. So our first speaker is Janice Siegfried. Janice, you're here. So I'm going to hand pretty much straight over to you. What I will just say to the speakers, if I can remember to do this, you will get a 2-minute warning. So for the speakers today, you'll have a 2-minute warning, and then you'll get an end. And I will come and push you off the stage if you don't end when I'm waving the end piece of paper.
Fair enough.
Over to you.
Good morning, everybody. I'm glad to see so many perky faces today. So hopefully you stay perky through my talk. I'm really happy to see all of you face to face. I think that's been a theme among our Congress, that yay, we are back in person and able to enjoy each other's company and all the great science that we do all together at once. And every time I look around, I see someone I hadn't seen yet before that I didn't know was here. So that's also exciting. So I will be leading us off this morning with a topic that's near and dear to my heart, which is the quest to develop automated systems for monitoring behavior. And I first started down this journey in about 2004, 2005, using pedometers on cattle before kind of going into developing systems for body-worn sensors for chickens, using computer vision for pigs, and now some for chickens as well. So I've been doing this for quite a while, and I'm still on the quest, if that might give you a clue as to how my talk is going to go. Before we begin, I want to throw a few caveats out there. First, this talk is going to focus mostly on livestock and poultry because that's what my team and I work on. So pigs, chickens, cattle are going to be where we start. Second, I'm going to be representing my team, who are a crew of talented experts in PLF development, and I'm an ethologist. So if I don't do justice to their brilliance, it is not their fault, it is mine, and I will apologize in advance for that. Okay, so let's get started with a couple of critical definitions. As people who work in the animal welfare realm, you probably appreciate the importance of starting off with making sure we are on the same page when we talk about these things. So as I started developing this talk, my colleague Thomas Norton said, "You're not really developing a talk on PLF, you're developing a talk on automated behavior monitoring." And I said, "What do you mean, Thomas?" And he said, "Well, when we think about automated behavior monitoring, what we're talking about is any kind of technology, whether we're doing video or audio or activity, that we're monitoring the behavior in an automated way. So some kind of technology is collecting the data for us, but then it doesn't necessarily take that data and turn it into actionable information that can be used by a commercial farmer or someone in the real world, right? We end up with a lot of data, but we didn't have to collect it. Okay, so the precision livestock farming piece, which some of you may get more into, involves using that data to then automate some management decisions or some actions on the farm that can help maybe target labor in a more efficient way. And precision livestock farming can be more than just monitoring behavior, right? We can monitor weight or body condition or animal temperature as well. So it's a bit bigger, And it's also a bit more designed to actually have a practical outcome that results in action and efficiency and improved welfare on the farm. So I'm a step back from that with the behavior monitoring. Okay, so now we're hopefully all on the same page with what I'm talking about today, but I will still say that behavior monitoring is important, right? I want it to be able to do research in my team. So hopefully many of you also feel the same way, that having automated behavior monitoring is still a big deal. Okay, unfortunately, I did not see this paper before I submitted my abstract. If I had, I might have thought, problem solved, no big deal, we're here, it's done. The future is now. We can automatically track individuals, we can identify them, and we can analyze their behavior, at least with monkeys and mice, as according to this team. So fortunately, the selection committee also hadn't read this article, otherwise maybe I wouldn't be giving this talk. So is this true, right? Have we solved it? And I get really excited when I see papers with titles like that, that also have videos like this, where, let's see if this plays. So you can see each of these macaques here is being tracked and their identities hopefully maintained even when those two macaques cross in the back. So that's a pretty impressive feat, right? We've got these monkeys being tracked in real time, their identities maintained even after they crossed each other and reappeared on the opposing sides. This is awesome, right? Okay, we can track animals. But then I always think, okay, what are probably the downsides to what's going on here? What is the rough spots the authors may have glossed over in the paper? Or more deeply, what are the accuracy and the precision and how long can you use this technology before it fails, right? So this program that they developed called SIPEC is 86% accurate at recognizing the identity of an individual macaque using just a single frame of video. It's pretty good, right? Well, humans are 100% accurate at it, okay? So we've already got 14% error right there in the initial recognition. And then if we think about like, can they recognize behaviors well over time, it's about 70% able to recognize these couple of specific behaviors that they characterized for the macaques. And when they used it in mice to try and maintain tracking of individuals over a period of time, each day the performance of that tracking dropped over time. And if they used the same mice in a water maze where they got wet, the tracking of the ability to identify the individual went to 0. Okay, so even for something as beautiful as this that shows like this really cool like proof of concept, there are problems. And if you start to have errors in your tracking, those multiply over time, right? So if you suddenly switch identities of an animal and then you are tracking the wrong animal now, but it's saying it's A instead of B, right? Your whole data set just went down the toilet. Okay, so, whoops, let's get past these mechanics. So ABM is only as good as it's trained to be. This is a really key point here, right? So they can present some really positive results, but until you dig in to exactly what they're looking at, how it was trained, who trained it, and what data they used, you really don't know very much, right? You can spin almost anything in an abstract in a positive light. Who's done that here before? Spin things in an abstract in a positive light when you had negative results. Oh, just me? Okay, sorry. All right, better not do that anymore. All right, so let's dig into some of these topics a little bit more. So developers with the right expertise and standards. So most ABM or PLF, if you go even further, is developed by a team, right? You can't do this typically on your own. And at the core of the team are the computer or the data scientists, the people who are doing the coding, the people who are building the algorithms for the machine learning that's going to detect the behavior and figure out how to process and handle the data, right? They're central. So you have to have those folks in the room in order to get this done. And then if you're talking about some kind of tech that you're building customized for your particular purpose, a particular type of sensor, rather than using an off-the-shelf camera, you probably have some engineers on the team too. And maybe even some agricultural engineers who understand that the real world where animals live is dirty, messy, changeable, and that animals like to break things. Okay, so maybe you've got that much expertise on the team, but it's fairly rare to have an ethologist with formal training in ethology, or even better, if you want it to have welfare implications, with that ability to make the connection all the way out to that level. So are the people who are developing this stuff to detect behaviors, do they actually know what they're detecting? Do they know how to describe the behavior the way we would? Do they know how to break it down into the components in ways that are important for us when we're collecting data. So if they say they're collecting tail biting data and then they call it aggression, how many of you would immediately shake your heads and go, oh dear God, right? Okay, so we have to start with the right expertise. And if you don't understand why that thing is not true, talk to me later. Okay, so we've got to have the expertise, and then we've got to have good data to work with from the start. So how much data do you have? How long? How many different files of data? How many independent instances? How many complete data sets do you have? And so what kind of context have you collected it in? Is it all been one type of pen system, or one type of aviary system, or one kind of farm? Or have you just collected data from the same pen of animals, even within a single building over and over? So what is your replication? And of course, it's even more critical when we think, how many animals have you looked at? Because we know that within a single barn of animals, there can be, each animal is an individual and does things slightly differently. Yes, a walk is a walk, but each animal has its own subtle differences in gait, right? And so we have to be able to recognize that variability and to distinguish between different kinds of behavior when that single variable behavior can be variable. So, and we also, if we're using something like computer vision, or actually almost any of these technologies, no matter what modality, we can have variation that also changes with animal age and gender and characteristics like that. So if I develop a computer vision program trained to detect in poultry, and I start with a chick and I train my program on the chick, and then I try to extend it for use in pullets, how well do you think that will work? Right? They are different in size. They are different in morphometry, right? Their shape has changed as they grow. And then if I extend it from what I trained on a chick out to a hen, oops, and God forbid I throw a rooster into the mix, right? So if I've trained it on a chick, is it going to recognize anything any of these other birds do with any degree of accuracy? Okay. So we have to think about what the data were that were used as the basis. And then we all understand the importance of this, right? We often have colleagues who think that, behavior, you just go out and you watch an animal. It's fine, right? You don't have to have any formal plan to this. You just go look and see what you see. And it's fine, you get data, right? But we know from our work that it's really important to set up your data recording really correctly, really rigorously, with really well-trained people. You develop a precise ethogram that says this is and this is not the behavior according to these characteristics. You train your decoding team or your observation team, and you check to see if they're equally reliable and if they stay reliable over time, because we don't want things drifting. Because the human, right, in this ABM case is the gold standard. We are the truth against which the ABM is measured. And if we are just a rusty tin can, then what, garbage in, garbage out, right? So we have to start with good training of the people that are actually doing the manual decoding, which is used as the basis for training the program later to detect what we detected, okay? So I've worked on teams with engineers, and two of my former postdocs are in the audience who had this problem, where we've been working with engineers, and we're like, no, we need an ethogram for the aggression. We need an ethogram for the aggression. You can't just say it showed aggression. What do you mean by that? What behavior subcomponents are you looking at? And so we had to keep pushing to get them to do this. Okay, so then we have, how much did you decode? 10 minutes? I got, last month I was at a conference where an undergrad was so excited that he decoded sitting in pigs. He trained ABM to detect sitting in pigs after looking at 10 minutes of video from one pen of pigs with 6 animals. I was like, okay, good, awesome. So we have all these questions about how much, right, in order to be truly representative, and how was it decoded? So when you have this data set, then afterwards, it has to have all of this information so that you understand the context, and you say, oh, okay, I'm reading this paper and they use these kinds of animals on this kind of farm at this time of day with these kinds of lighting conditions. Maybe it will work in my barn, right? Or maybe, oh dear, I have totally different light. I'm using a different coat color of animals. This is not going to work. So you have to understand all these parameters, and these things are typically not reported in ABM papers, okay? So one of my pleas to everybody in this room is, if you're working with teams on this stuff, please make sure that these details are provided in the methods section. Sometimes you're lucky if all you get is the species of animal that was studied, okay? That is not sufficient information to know if you can replicate or extend it. Okay, now here we have a very non-trivial problem. How was the ABM validated? And by validated, I mean, how did we test this algorithm, this process? It's actually as good as it's claimed to be, that it does what it's supposed to do. So two key questions here are, who did the validation? And which data did they use to validate it? The most common strategy, I would say in over 90% of the cases, is a process known as internal validation, where the same team takes a data set and they divide it randomly into a test set and a training set. And they might decide the proportion, maybe it's 50-50, maybe it's 70-30, whatever. But basically they are training, the same team is doing the training, and then they take the remaining data that was pulled out and they test, right? More robust approach, of course, is if a different team with a whole new set of data then tries to see if this can work. So you have people not familiar with how the ABM runs, trying it novelly, right? To see if it works for them, or if they're like, I have no idea how to make this run. And then you have a completely different set of data, so you can test generalizability and robustness, right? So external validation is better, but very rare. So if you have this internal validation going on, well, how can you do better? And there are ways that you can do this. You can go beyond random validation to some kind of blocked strategy, because all of the data sets we work with, they have underlying structure. Animals change over time, or there are differences between pens that we have to account for, and which we would account for if we were doing statistics, right? So we can account for that in how we parse the data for training and testing, and that will at least make it robust. So for example, you could take a data set with animals at a younger period and see if when you train the ABM there, you can predict the same level of accuracy with that ABM for older animals, okay? So I have an example from our group. Our PhD student, Junjie Han, compared validation strategies, because you look in the literature and you're like, wow, 90% accuracy, 90% precision, this is great, right? Or sometimes, as in the left panel here, those recalls and precisions almost hit 100%. Like, this seems like it's perfect. This program works beautifully. So what Junjie had done is he trained an ABM to detect the behavior of 2 pigs in a single space feeder. So we have an automated feeder designed for 1 pig, but of course, other pigs like to try and come in and knock the first pig out of the way, or maybe just harass the first pig in the feeder. So we were trying to detect, how often does this happen? Does it cause problems in feeding and intake and all that stuff? So he classified things as no contact between the 2 pigs, gentle head to body, or levering, where the behind pig shoves the front pig up, or mounting. So those are the abbreviations down there. So when he just selected the data randomly into a 50-50 data set, we got these really great numbers. But when Junjie took the first data set and compared it to data we collected 3 weeks later as the validation, you get the block by time panel that shows up here, where especially precision drops pretty dramatically for something like levering. So now the program's only 40% accurate at detecting levering behavior, okay? So just by looking at pigs 3 weeks later, when they're a bit bigger and their proportions are a bit different, suddenly things change in how good this ABM is. This is a confusion matrix, and this is something we can use to try to tell where the error is coming from. So the diagonal axis right here, this is when things match up between the target and the prediction. Okay, so we have the ground truth, and then we're seeing how well the prediction lines up. So when things fall off the side of the axis, like here, that shows a misclassification. So the common misclassification that we were finding was that head to body contact was being misclassified by the program as either levering or mounting, which were more severe behaviors. And another common problem we saw was that head to body and no contact was being misclassified as the pigs grew. So simply by looking at our data differently, like using that later data set as the test data set, we found that there were some errors in how robust the program was at truly detecting those behaviors in different age classes of animals. Okay, so another problem is that ABM solutions are often too focused, okay? So we develop an ABM to detect one specific type of behavior or one specific type of problem, right? And that may be really necessary. Maybe we're trying to reduce cannibalism or tail biting, right? Something really problematic that has a big effect. And we did some work in our team, working with Thomas Norton's crew and Chen, his postdoc, where we detected aggression versus no aggression in pigs in a nursery. Or we detected feeding behavior versus no feeding behavior for the pigs in a nursery. Or we did drinking versus no drinking behavior for the pigs in the nursery. So we could classify each of those three conditions quite well against the background of the other behaviors. But that's pretty simplistic, right? If we're trying to look at like time budgets of animals and how patterns change over time and kind of a really complex look at the whole animal's life, not just this one little aspect of something that it's doing. Well, so we have this problem, but maybe we can combine these things, right? Maybe we can put the algorithm we used for the aggression together with the feeding, together with the drinking, and then we can start to actually get a more robust time budget from all of these pigs in the nursery that accounts for all their variation in behavior. So there's starting to be a bit of progress in this area, but we're still a long way off from just having a pig behavior detection program that we can plug and play that will detect all the things that piglets do over the course of a day in the nursery pen, right? So that's something probably some of you have encountered, and I know in the talks to come later, there are some talks that demonstrate some nice solutions geared at one particular problem. So for me as a behaviorist, one of the big kind of bummer take home messages is that there's limited plug and play ABM. And what I mean by this is I'm not a coder, okay? I can't program diddly squat. Like I'm lucky I can put my passcode in my phone, okay? So I can't take an algorithm written in Python or R or something and actually modify it to fit my situation. I need an app with a nice graphical user interface that I can put a couple key variables in and then hit go at the bottom. And there's not that much out there, right? Maybe if you're working in the cattle area, you are far luckier than the rest of us because there's much more of this for cattle than there is for any other species. If you're in poultry, you're just out of luck, sorry. So why? Why is this the case? Come on, ABM developers, get with the program, literally. So back to that problem of small data sets. A lot of ABM, if you do a search through the literature and you look at how big the data sets are, most ABM programs have been developed using less than 50 animals. Okay, in many cases, less than a dozen. So that's a problem if, let's say, they built it to detect those like pigs in those little nursery pens that I just showed you. And now I want to extend it to finisher pigs in bigger pens, or maybe on straw, or maybe now on this gridded flooring, but like with 1,000 pigs in the room, or maybe in an electronic sow feeding system with barriers in the room, or God forbid I go outside in the mud and the actual natural light, right? I can't take that ABM that was built on that small data set, even if it was plug and play, and turn it out there. The other problem is we don't have a lot of stuff that's commercialized, right? It hasn't yet hit the marketplace where we can just go out and buy it. It's all either built for customization, or you work with a researcher who is in the computer science realm that can build it for you. And I went through this process with a chicken Fitbit, essentially, and 6 years later, I still don't have a chicken Fitbit that I can just put on a chicken and use to collect behavior research data. That's all I wanted. Anyway, I'm not bitter, it's fine. So there's many that are not commercialized. As I said, in the cattle realm, there's probably more because we also link them to robotic milking systems and to milking machines so that we can get data on things like estrus detection or health problems like ketosis, or just whether or not we need to increase the feed on a particular animal because her weight is changing as she's going into lactation. This is an example of a commercial product for pigs, Sound Talks, where you can actually do cough monitoring of pigs, but at the pen level, right? And that's often not refined enough for those of us that want to do individual animal kind of work. And there's an example of a pedometer in cattle from ICE Robotics. So there are some tools out there, but they're often fairly limited in application, despite the fancy web pages that may advertise, these ones do automated behavior monitoring. And then you look at the list of behaviors that are monitored and you're like, oh, mine's not on there. Or that time budget is really flimsy. Okay. So another problem that we're facing right now is the artificial intelligence, the AI that we're using to create the ABMs. It's not yet as smart as we are, which personally I still find comforting and reassuring. But it limits us in terms of what we can do, right? So living animals are complex. you have all of this stuff that changes in an animal as it's behaving, let alone as it's growing, maturing, lactating, gestating, or whatever. So our bodies, right, they almost deform and change proportions as we go from one behavior to another. And certainly for some animals like an octopus, they take that to the extreme with how much they could deform as they're performing a single behavior. So when you have an AI that's trained to maybe detect a can rolling or cans occluding each other or cars changing direction, it's still a very static thing that is changing what it's doing. The car doesn't change proportion as it goes around the corner. Maybe the wheels move a little bit, but it doesn't arc, right? The body of the car does not change, but the body of a pig as it goes around a corner does change. So computers are not as good yet at detecting this variability, right, in the animal side of things. And of course, all of us that have worked in animal environments with trying to get cameras in the right place, we know this problem of occlusion, where the feeder is in the way, the drinker line is in the way. Oh, wait, the other animal is in the way. And they're always in the way, right? How many, we have piles of animals in these spaces. So they pile up and then they separate. How do we keep track of them as they cross over or under or through each other? We can often do it fairly well, but the computer still doesn't do this well. Strangely, they can do it better with like mice and fruit flies, which I'm like, how do you tell them apart? And then we have things that leave and re-enter the field of view. Sometimes it's most economical for us to have a single camera, but that means that you're going to see animals coming and going, and can the computer pick them back up? And some of these problems we're making headway. We're just maybe not perfect yet. And our brains, we're capable of doing several things yet that AI can't. And we're very good at combining all of our sensory information really quickly all at once, right? So I can tell a pig coughing because I can both localize the sound and see the body posture of the pig and its motion at the same time and put those together without even thinking about it, right? I don't have to cognitively, consciously think about it. We're also using multiple types of learning and memory, right? Different kinds of induction and deduction to come to a conclusion by putting all these little tiny facts together to say, yep, that's that behavior. And different kinds of previous memory and recall. And all of these things are still a bit too complicated for a computer to do as quickly as we do. So real-time monitoring and detection is still far easier for us than for a computer system. We'll get there probably. Okay, so sorry, this was a bummer of a talk, right? Now what? How do we actually get to where we want to be? How do we get to these miraculous little thingies that we can plug in and say, detect the behavior for me, right? So we want to accurately identify and track, especially unmarked animals, right? If you've ever done studies in a big group of animals where you have to track individuals and you have like 300,000 brown chickens that all look alike, oh, this is a problem. Okay, so how do we get there? Especially when we house them in large, dense groups that are, we don't have a lot of space between animals. So how do we identify and record the frequencies and the durations, but also the intensities and the patterns and the variations in the behavior? So counting things and recording durations is one thing, but getting to the more complex stuff of what this all means in terms of patterns is much harder. And then another thing is, how do we localize where this is happening and who it's happening with? And this is really critical for so much of the social stuff that we look at with the animals in our groups. Who's doing what together? So when are we going to get there? When are we going to have this plug and play AVM that eliminates the hours and hours and hours and hours and hours and hours, hours? You get the picture of us observing and decoding, right? When? Well, there are a few. I can't give you that answer. If I could, I'd go out and invest in the stock market right now. Good. But we can do a few things that will help us. So first of all, on our side, we can get a little bit more training in these computer and data science areas, right? We can gain a little more competence. We can figure out how to do some rudimentary coding, right? We can figure out what it means when we're looking at a machine learning algorithm and they're talking about a deep neural network that has this many nodes. Yeah, we can start to get there. Some of you are shaking your head like, no, do that. On the other side, then maybe we can do this. We can create intuitive AVM. So maybe part of it is we learn it a bit better, but also we get AVM that actually works with us non-expert coders a bit better. So developing easier interfaces like apps, or using things like natural language processing, where I could say, okay, go out and detect feather pecking in this chicken population to the program. I say it, it interprets me correctly, and it does it, just like a grad student would. Sorry. Okay. Another thing we can do as ethologists is we can actually help generate some of the data sets that computer vision people or whoever the ABM developers use, right? We have been decoding data for years. And some of us have the video files or the audio files or the activity files, plus all this annotated data. So can we put some of that together and share it so that other people can use it and then make detection programs from it? So I put up here a series of different cattle pictures, right? And I haven't even captured all the variability that's possible in a cattle population or the types of cattle housing out there. But what you can get from this is, right, we can't just train stuff on one herd of Holsteins in a freestall barn or one group of Black Angus out on a pasture. We need a lot of stuff. We need calves, we need cows, we need steers, we need bulls, we need indoor, we need outdoor, we need different coat colors, we need horns and no horns, udders and no udders, right? We need a lot of stuff. So we need variation. And many of us who've been collecting data from different types of animals from around the world, we have that. We have local indigenous populations, or we have variations in coat colors and things like that. And so we could contribute. So we have more animal data, more variation, and we annotate, right? We know all those important things about like time of day and age of the animal, breed of the animal, right? Things like that. And then we need to share it. And it is getting easier to do this in the cloud, right? We can do this more easily. And there are great data sets out there that AI people around the world use all the time for like facial recognition or training autonomous vehicles. But these public data sets, when they have animals, they're typically like dogs and horses in the family environment, or maybe like backyard chickens. They're not animals in production settings. They're not animals in many of the contexts that we need. So we can make a little bit of progress using some of these data sets, but we need our own kinds of animal-based data sets that meet our criteria. So we did a search. Junjie, again, as part of his PhD, did a search to see, so what's out there if we wanted to do some ABM using animals, and he specifically focused on computer vision, and he looked at cattle and pig data sets, and he found 20 that were publicly available. So all the images and video, plus all the annotation and kind of the labeling for the context of things like that. So 8 of them were for entire body detection of the animal, 4 were for specific body parts, 8 did animal ID, and all of these are important for the behavior part, but only 6 of them went as far as what's the behavior. So we had 5 data sets from pigs and 1 from cattle that we identified. And here's just a little bit about the details. All of these are available online, so you can search for them using the data set name and find them if you wanted to use them to develop some ABM. And they were used for published papers detecting these types of behavior that are listed in the behavior type category. And so you can see that in at least 3 cases, we've only got 2 things detected: lying or not lying, investigating, exploring, sitting, standing. And in a few cases, we get to 4 to 5, or maybe even 6 behaviors. But that's still a pretty small number of behaviors for the entire repertoire that these species have, right? So there's work that's being done. And then if you look at how much was annotated, then you can also see that in some cases there wasn't very much. In the pig position and posture data set, only 305 images were used. That's not a lot. That's probably like 10 seconds of data, 30 frames per second, okay? So we have some small data sets that are out there. So one of the things we're trying to do to combat this is Juan Steibel, one of the kind of leaders of our team, is working on this project called FACT-CIN, and it's a coordinated innovation network where we're trying to put together groups of people working specifically in the computer vision space to solve animal agriculture kind of problems. So we're building reference data sets that we're going to generate and share. We're going to annotate. We're going to provide baseline analysis. And we're also going to develop standards for how to create these reference data sets. So if somebody else wants to contribute one, here's the information you should provide along with your data set. Here's how you should package it, et cetera. And we're also going to provide some help on evaluating results. What validation strategy should you use to know how good it was? How should you go about that? Okay, so conclusion. So we need your help. right? To make ABM, all of us need to contribute our expert data sets so that we can actually get stuff that decodes it the way we want and gives us the results and information that we can use. So if you've got data sets that are lying around and you're just like, I just haven't figured out how to upload those 54 terabytes of video, that would be me. I have one of those. Try to get there, try to make that a priority. And then work together with ABM teams and try to convince them of the importance of ethograms and rigorous training and more animal variability in the data sets so that we get things that are more robust and can be generalized. With that,
Right, a very long round of applause for a great talk. So whilst people think about questions, I've just really got a comment to make, and I think it's fairly apparent. You're probably familiar with the Gartner height curve, are you? So it's a curve of sort of development of technology. So I think the engineers led us through this peak of inflated expectations. You've actually brought some realization that we are in the trough of disillusionment, which is one of the sort of the bottom bit, but actually you then go to the slope of enlightenment. So actually I think you've got a great way forward, and ethologists, we really do need to engage with this program. I think the engineers, they do think this behavior stuff, oh, it's all too easy. They don't realize what we need to do. So open for questions. Yes. Again, if you can just say where you're from.
Hi Janice, Lucy Usher, Newcastle University. Thanks for a nice talk. I'm interested in what you were saying about ethograms and time budgets, etc. How much do we as ethologists need to adapt our methods and our approaches to these new challenges and opportunities from automated behavior analysis?
that is a beautiful question, because one of the actual sticking points with going from us humans doing kind of intuitive, like looking maybe over a series of images to get a behavior versus the computer is that the time scales and the features that we're using to get there are very different. So, if you have to break things down on a frame by frame analysis for the computer program, you're seeing very static things. Yet when we're doing behavior for our observational studies, we're typically doing a kind of a moving, changing thing as we process the behavior, like something like dust bathing, right? Which can be a fairly long sequence of multiple small sub-behaviors and postures and movements. So it's really important, I think, to have that conversation and think, how do we break this apart into the right pieces so the human decoders do a good job of giving the computer scientists the data they need to do the training at the computer scale? Great question, thank you.
Right, we do have a second question, which is just over the other side. Basil will be third. We don't have any questions online yet, so for the Zoom, for those of us following us on Zoom, put your questions in the Q&A if you have any questions, and we'll come to you, but we don't seem to have any at the moment.
Mike Descano, University of Bern. Thanks, Janice, great talk. I was curious, the data that we can generate with these systems is also very, very novel, whereas a grad student historically could generate 20 minutes of video over the project. Now we can have hours and hours and days of precision location. So also, do you have any thoughts on how that data should be analyzed, or even does that require a new school of thought or anything along those lines?
No, I think that also provides opportunities for us to expand how we think about things, right? Maybe a little bit of a paradigm shift on our end, because we've often wanted to just break things down into simple frequencies or durations, right? And we lose a lot of subtlety and like animal reality in that process when we just kind of condense into averages and things. So we do need that. And I know that, with some of the team you've been working with at Bern, you guys have come up with some pretty novel ways to look at time series kinds of data and to kind of keep track of some of that complexity over time. So we need to, I think, be willing to expand our skill sets. And I know sometimes the realm of the computer side of it, that's not why we got into applied ethology, right? We wanted to watch the animals. We wanted to be with the animals and to do things with them. So the fact that we sometimes have to engage in so much tech or math to get there, let's just be honest, math is tricky, right? But we need people with those kinds of skill sets too. And sometimes we have to forge longer term relationships. You can't just do these things over the course of a quick project and everybody understands everybody and then you've come up with a eureka thing, right? So some is forging longer relationships.
Short question, please. Short answer.
Yeah, Janice, you talked about individual tracking and moving to larger groups. Can you talk a little bit about sort of how important it is to have a fixed identity in these large groups? Because there's also approaches now to look at pen level activity or stuff like that. So.
Yeah, so we know individuals kind of a necessary thing at the welfare level, right? Welfare is experienced by an individual, not by a group. So when you look at the group average for welfare, you can miss all of that variation or the tails of the curve. So, but then when we're faced with commercial, you know, I've been on laying hen farms in the US with 2.5 million chickens on a single farm. Yes, that is true. And they're even bigger in other parts of the world. So how do we feasibly keep track of that? And if we could collect the individual data, what would we do? So can we do smart sentineling for some individuals, but then have group stuff for the majority? Maybe a blended approach is where we need to think about. Sorry, that wasn't that short.
No, that's good enough. Well, you led us bang on time to finishing because we have actually got some announcements. But first of all, let's thank Janice again. So before we split into the two groups, there are some quick announcements. So I'm taking my chair's hat off and putting my president's hat on, just to say that the ISAE AGM, our annual general meeting, will be at 5:30 p.m. in here. So we have got to change the constitution. We're supposed to give you a printed version of that according to the constitution. So that is up on the notice board by the entrance to the other room. Okay, so have a look at the constitution change. Also, we have got some open council positions, and we've got the details of a couple of the applicants up there. So have a look at that. We also have a questionnaire went out quite recently from our Equity, Diversity, Inclusivity and Accessibility, or EDIA for short, committee. If you haven't completed that, to make it simple, there's a QR code which you can scan from the notice board. Miro, do you have some announcements?
Just a couple of algorithms for human learning, not machine. Just what we learned from yesterday. So just try to apply to today. Please, all the speakers that have their presentations and they have oral talks, just be 30 minutes before your session and contact with the technical team in order to check your presentation. Is it okay? Is it functioning? Everything and so on. So we don't waste time during the session. I would like to ask the chairs that before starting the session, please check who is present, who is not. We have online presentations, we have physical presentations, we have video records. So we need to, the chair should know, is there any presentation and what kind of presentation is before each chair, each session. Please be within your given time. I just forgot the papers. We will spread this for the chair. So you will have, yes, 2 minutes warning and a finish. So be careful and keep the time in order to be within the time slot. About the posters, my famous one. Posters are available till the end of the Congress. There was some rumors that we will move them. No, we will not move them. So they will stay in the room till the end of the Congress. Please use the Zoom rooms that are online. Either you are here, you have all the poster presenters, you have your Zoom room, all the poster presenters that are scheduled for today is having their own Zoom rooms. Please visit them and make this channel much more busy during this Congress and give an opportunity for the presenters to talk with them about their work. For the online posters, so posters that are not here, you should visit the Xordo platform where you upload your presentations, your PDFs, and so on, so you can check. Over there in the front of the 2 poster rooms, there is a list of posters with their numbers that are online, so that you will not find it here, but you will find it in the Xordo. So you can visit them. And please, the next slide. And now some technical things for today. The list of departure. So according to your a scheduled time, we make new lists, which will be available after this session. You will find it in the announcement board. So please check when is your time for departure and does it fit within that time slot. If not, please find an alternative of what we are offering. We cannot like choosing for each person. Can you imagine 200 cars to go from here? So for today, what is planned? The Ohrid city tour is planned to start at 6 o'clock in front of this hotel. So in front of Metropole, there will be buses, and we will leave at 6 p.m. After the end of the city tour, we go. The end point will be the place where the national dinner will be. So those that are having the national dinner, that are registered for that, will stay there. For the others that are not, we will provide a bus that will bring them to the hotel. For the rest of the people that will stay at the national dinner, then after the national dinner, you will have an opportunity to use bus to come here or to stay and do whatever you do. Okay, so that's it. Thank you.
Right, so it's now time to split. So we have actually taken up the 5 minutes we allocated for that. So who's chairing the next session? You? No, somebody. I'm chairing this one. Sorry. Who's chairing? So we're going to have we're going to have 5 minutes. Okay, so we're going to start in 5 minutes to let the other room get set up. So hopefully, can somebody make sure the chair of the other session is aware of that? Yes, they are. Right, we're going to just giving you a 1 minute warning. Just wrap up your little conversation and then we'll be going in a minute. I'm okay, I've got them. Right, so I think we need to continue with our precision livestock farming session. So we've got 3 15-minute talks. So again, you will get, just for the speakers, 12 minutes, sorry, at 10 minutes, you'll get your 2-minute warning. Please try and wrap up 12 minutes to give 3 minutes of questions. I will push you off the stage at 15. So we've got 3 talks, 15 minutes, and then we've got the posters. So first up is Juliet, who's going to be talking about Digitech as a boundary object. And I'm hoping you will define a boundary object because I'm intrigued to know what it is. Can we have Juliet's slides, please?
Hello everyone, I'm from the University of Reading, and today I'm going to talk about some of the work that I've been doing. Closer, okay. Okay, so yeah, and today I'm going to talk about some of the work that I've been doing as part of my PhD project. So I'm going to talk about the potential of digital livestock technologies to enhance farm animal welfare using the concept of boundary objects. So digital livestock technologies, which here I include simpler smartphone applications to more sophisticated PLF technologies, are often viewed as a key response to some of today's most important challenges linked to population growth and increasing concerns around sustainability and animal welfare, as it can help farmers in monitoring their livestock and to detect changes in behavior and or physical parameters, and to detect health and welfare compromises at an early stage. But despite the many potential benefits of these technologies, the extent to which they can actually help improve animal welfare is still relatively unclear. And this is partly because, as we know, animal welfare is a complex notion to define. It can be understood differently by different people, and that makes it somewhat challenging to determine the extent of these improvements. The other thing is also that many of the commercially available technologies often focus on health parameters, not so much on promoting positive aspects of welfare. So we suggest that determining the ability to of DLTs, or digital livestock farming technologies, to enhance animal welfare should not only focus on their ability to detect these health compromises, but also on their ability to foster learning around this notion and to promote positive animal welfare. And this may depend on their ability to act as boundary objects. Boundary objects are objects that are plastic enough to be adaptable across multiple viewpoints, yet they maintain continuity of identity. So these can be material objects, or theories, or concepts that share a common definition, but that may be interpreted differently by different people. The DLTs were conceptualized in previous studies as boundary objects through which stakeholders can collaborate and co-learn during their development. So here, by acting as boundary objects in the context of farming, the use of DLTs could help promote or facilitate discussions between stakeholders, like between farmers and advisors, for example, and potentially to generate learning and a shared understanding of the notion of animal welfare, which in turn could lead to changes in management practices that would improve welfare. So, so we suggest that these impacts could be greater if these technologies could help promote a deeper reflection on farmers' underlying values and beliefs, which relates to the double loop learning concept, as opposed to being limited to improving existing strategies which relate to single loop learning. So in other words, single loop learning relates to the know what and the know how dimension of knowledge, in contrast with the no Y dimension of learning, which relates to double loop learning. So basically, this study is aimed at exploring how DLTs can promote learning around animal welfare and what are the potential impacts on management practices. So the study was based on 2 case studies during which 2 different DLTs were tested, and we conducted interviews with case study participants, which include those using the technologies and the developers, to gather their perspectives and experiences. Just to give you a quick overview of the case studies, the first one, which I will call case study A, is looking at a camera-based system that was developed and tested on 11 dairy farms in the UK, which aimed at automating body condition and mobility scoring as a way to reduce the possible biases and errors that exist when conducting human assessments. And also the technology is aimed at allowing farmers to spot changes in these conditions at an early stage. I have to clarify that there were many technical issues during the project, which means that at the time of the interviews, only 2 farmers were actually able to make full use of it. So I will make it clear when I talk about actual experience of farmers or more their expectations of it. And in case study B, it was a smartphone application that was developed by a UK Research Institute and licensed by a UK retailer to help farm assessors conduct assessments on animals' emotional well-being. This app can be used for different livestock species and is based on descriptive terminologies like relaxed, happy, or distressed that are specifically selected by groups of stakeholders. These descriptors are scored on the app after the farm assessors observe the animals using sliding scales, and statistical integration then produces a graph of overall patterns of emotional expressivity that allow farmers to sort of figure out where they sit in comparison to other farmers. So in these cases, so both technologies actually acted as boundary objects in this case. And first, because they allowed to open discussions between different actors in both cases. So in case study A, participants mentioned the benefit of the technology to allow advisors to tailor their advice based on the data generated to help farmers in decision-making to boost productivity and animal welfare. In case study B, in a similar way, the app was seen as a tool to connect stakeholders, helping them articulate what they were thinking internally. So one participant, for example, said how the app helped them put words on feelings and thoughts that they had, a little bit like the quote that is displayed here. Both also had the ability to bridge gaps, the gap that exists between consumers and producers. So in the first case, participants mentioned how it could help provide evidence on the claims that are made around welfare as a way to improve trust in the farming system. Whilst in the other case, participants mentioned how the app can be used to demonstrate care and to reassure consumers, especially as it's a method that that consumers can relate to since it's using non-specialist language. And it's also it was also seen as a way to demonstrate that the emotional aspects of welfare were taken seriously, and also to open discussions with farmers around that subject, which they are not necessarily always used to. So both could help facilitate these connections, and both also had learning outcomes. In the first case, the camera was seen as a way to allow farmers to act at an early stage to better manage lameness on farm. So participants mentioned how it could help detect cows that are slightly lame, which some of them mentioned how they would ignore that in the past. So one farmer said how who was actually using this technology, said how it helped them make better use of their time and to do a better job by being more proactive and better organized. In case study B, the tool was seen as a way to link emotional expressivity with other metrics in order to work out potential issues on farm and to see where improvements are possible. It was seen also as a tool to drive change and to encourage improvements towards positive animal welfare. So one participant, for example, mentioned how they use the app to and try different types of enrichment or lighting conditions as a way to then advise farmers on ways to adapt their practices to see improvements. And then finally, one participant also, several participants also said how they had learned more about animal emotional expressivity and looking into behavior. And so some of them suggest that it could be a great tool for training on farm. So both technologies actually differed in the extent to which they promoted double loop learning. While in case study A, the camera made one farmer question the level of welfare on their farm, others, when asked about whether the use of the technology made them have a change of perception of animal welfare, one of them clearly said, well, I haven't learned much. And another one said, well, we were considering animal welfare before, so not really. And in contrast, in case study B, several participants said how the use of the app made them think more deeply and more actively and to actually look at expressions of behavior, stimulating them to ask why certain behaviors occurred as opposed to whether or how frequently they occurred. So several of them talked about how it made them think about the animals' perspectives and triggered a shift in attitude from an emphasis on health parameters to a focus on emotional states. So in both cases, we saw that the technologies help facilitate connection, bridge gaps between consumers and producers, and in both cases generated learning through better health and welfare management. In the first case, through to learning about the importance of animal emotional expressivity in the second one. And so, well, both could lead to significant welfare improvements. Their ability to foster to generate questioning of existing strategies actually differ. And so more and more sophisticated technologies are being developed to spot health and welfare compromises. However, ensuring good animal welfare, as we know, is beyond, goes beyond minimizing negative consequences. And we've seen in this study that using the latest AI-based technology doesn't always mean that it's going to be more beneficial in terms of impacts on animal welfare. And that basically, whilst we can't ignore the benefits of smart technology, if there could actually be a shift in mentality, the impacts could be more significant. Obviously, that means that that the management practices must be adapted accordingly, and that's a challenge in itself in terms of practicalities and financially, which also shows that it's important to work with farmers when developing these technologies. So to conclude, in thinking about DLTs and their potential to improve animal welfare, the focus should be perhaps more on the potential learning outcomes as opposed to how technology advances. Thank you for listening.
Right, thank you for keeping perfectly to time. So if you want to change rooms, do so now. Do we have any questions for Juliette? We have one at the back. Microphone is coming again. If you can just say who you are, where you're from.
Hi, Agnes Balfan from World Animal Protection. Thanks, Juliette, for the nice talk. You mentioned that the farmer could enter the data and then compare the result with other farmer, if I understood correctly. And my question is, did these apps also allow farmers to talk to each other, are part of seeing what the other are doing, or will be a potential development to put them in contact? Thank you.
Thank you. A very good question. So at the moment, the app is being tested, and it's mostly the farm assessors who are using it. So at the moment, I don't want to say anything wrong, but I don't think farmers are able to access those graphs. But the aim will be, yes, that they will be able to and that was also what I was trying to explain. Maybe I didn't really expand on that in the facilitating connections. Is yes, it's also. I mean, it is meant to then make farmers talk to each other about maybe maybe they might see that okay, I'm a bit lower on that on that graph, and why is that? So some participants actually talked about this, how it could help ask, well, what are you doing that I'm not doing, and so why are you in this state? But I don't have, I think, concrete examples where they actually discuss.
Yeah, we have time for one quick question and a quick answer, please.
I'll try my best. Hi, I'm Clara from University of Bern. Thank you very much. My question aims at the bias that we sometimes have when we do case studies, that we get farmers that are more willing to apply new things. How big do you think is the willingness of the average farmer to apply such technologies?
You mean both technologies, or
just
general?
Of the newer, yeah.
Well, that's also a really good question. And yes, there's definitely been, especially in case study A, for example, where farmers volunteered to take part in the project, so they were automatically, let's say, more open to it. And in the second case study, they didn't really choose it. Now, in terms of how willing they are, I mean, that's a wider issue with PLF adoption, which is another aspect that I'm focusing on, and I'd be happy to discuss this with you.
I'm going to interrupt that because that's a long question to answer.
Okay,
so let's have that discussion at another time.
Okay, we can
So
have
thank you very much, Juliet. So next up we have Roger from Spain talking about geolocation in livestock. So again, can we have Roger's slides up, please? We have Roger's slides there. No, yeah. Yeah. Or you need to do something on here, maybe. Right, we'll just wait for the slides to come up on the screen. Are you in presenter mode? You are. Off to you, Roger. Yeah.
Okay. Good morning, everyone. I'm Roger, and today I will explain some of my PhD results that we work on how the use of new technologies, in this case, geolocation collars, can help us to assess the health and animal welfare state in extensive livestock farming. So first, I will start with some background. How probably most of you already know, extensive production is characterized by the access of free pasture for the animals, as you can see here in this picture, in contrast to intensive production. In my study, it happens during the spring and in the summer when the animals are in the mountains. So for the reasons, many people think that in this kind of production, the animal welfare is already guaranteed because they are grazing in their natural places and have the possibility to express their natural behaviors. And although this is certainly true to a great extent, the problem is that we cannot check them, and we cannot check them regularly, so we don't know how they are. So, in other words, the advantage of having the possibility to express their natural behaviors have as a disadvantage the absence of control or protection for illness, lameness, the bad forage quality, or even for predators' attacks. So in extensive livestock farming, arid and mountainous areas, to monitor them are very difficult and challenging due to the large of the area and also the difficult access. For these reasons, we wanted to use the geolocation colors in this case to assess if we can locate the animals and know the state of them. Okay, because this becomes critical because to check them is very expensive. Maybe they takes a lot of time and it's laborious. So these views, although they're magnificent, makes the farmer job very difficult. So at the end, we wanted to change that when in a scenario that the farmer doesn't have any control to another scenario when the farmer have a completely control of them and have the possibility to know how they are. So the aim of this project was to see the capacity of these technologies, the geolocation colors, to control the movements and the location of the animals, to verify if it's possible to control the state of that animals, and do that in arid areas, mountainous areas in the Spanish Pyrenees that are about more than 2,000 meters above the sea level, and see if we could integrate all this data in an application, in a mobile app application, and if we could create a kind of warning notification system. So what we do, we contacted with 14 farmers from the Alt Pirineo Natural Park. We choose this natural park because it's where the extensive livestock production have a strong presence in there. And we locate 228 geolocation colors to cows, horses, and sheep. As you can see, cows have more colors because they have also a stronger presence here in the natural park. And here you can see an example of the views of the place. We recollect the data from 2 years, 2020 to 2021, during the grazing period. So how exactly works the color? Well, as you can see, the color is this dispositive that it surrounds the neck of the animal and is set to send a signal with the localization and the superficial temperature. Okay, this signal is sent through a sigfox coverage that is sent into a cloud, and then we can see through the application, as you can see here. Okay, and also we are able to download all the data without the necessity of retrieving the color. Well, with this information, we were able to track the movements of the animal every day, so we can have a kind of activity, and also the superficial temperature. Okay. Also, I would like to remark that we use sigfox coverage because in these areas they don't have a mobile connection. Then we have to create another kind of connections, installing different antennas over the natural park. So, in fact, what we want to see if we could detect different situations, okay, any different welfare and health concerns like infections, illness, lameness, predators contacts. So in fact, what we do here is to detect this situation with the help of the farmers and see and do a kind of retrospective analysis to see if we could find significant difference between these measurements, the activity and superficial temperature, over different individuals or over the time. In this exposition, I will talk about 3 different cases that it happens in cows because are the clearest ones. The first case was a case of mastitis that actually was the app itself who advertised the farmer that something was wrong in that individual due to the low activity, as you can see here. So the farmer, who was also veterinarian, go to check them in the mountains, and he could confirm the case of mastitis. He could treat it and assess and treat it. So you can see how the month prior and the month after the activity comes to normal levels because the mastitis was already treated. And also we saw a significant difference in activity if we compare with the other hair here in brown. Okay. Well, unfortunately for me, not for the farmer, of course, we only detect one case of mastitis over the 2 years, but that's why we need not to recollect a lot of that. Anyway, we didn't find difference on superficial temperature. So the second case was a pregnant cow that the farmer predict the day of the perturbation around the middle of September. And we wanted to see if we could predict exactly the day to be more accurate. So first of all, we saw the activity over the different months. And we see here, actually in September, an increase, but was not significant different. And happened the same over the weeks of September. No? There's still an increase in the 19 and 20, but was not significant. So we tried to go to do a deeper, closer analysis on the daily basis, and we could find different significant difference in activity in some days. Okay, but was not really good, reliable information. So what we do here is to look at the animal on the different days, and we see on the 15th and the 16th how the animal is slightly farther away. It's a common, as you know, a common behavior in pregnant cows to have their perturbation. So the point here is that if we are able to combine this information, the activity, and also the location of the animal, maybe we can find the day exactly of the perturbation. Finally, the first case was a predator contact. In this case, the farmer found the animal dead with the collar broken, okay, and also with marks of being eaten by a bear. But here we don't know if the cows fall accidentally or due to the bear contact. So we analyzed the data, and we not only see an increase of activity the day an incident, comparing the day before and the day after, but also we have seen difference with the other another herd that was farther away of the possible incident. Okay. So in the next slide, we can see the movements, the location of the herd that was possible in the near of the incident, and we can see, like, here's the day of the incident, how the animals decide to move further away. That also explains the increase of activity, and also go in a higher elevations. That's an uncommon behavior that probably it will be explained if they have been in contact with a predator, like in this case, a brown bear. So in conclusions, these preliminary results, and I will remark that are preliminary, seems that we are able to have the health and welfare state of the animal. We can monitor them. Anyway, we still need recording more data because we only detect a few incidents, and we don't know if it was for a problem of the accuracy of the system or for a real low incidence. We didn't find any difference in superficial temperature, but I would like to remark that it depends a lot on how is the position of the dispositive and the contact with the skin. Also, the next step, it will be to create models, modelize these activities to have a better reliable results, and also take into account how important it is to have a good coverage in all the area to try to don't to lose data. And that's it. Thank you for your attention, and I will be pleased to answer any question.
Right, thank you, Roger. You've also kept perfectly to time. That makes my job so much easier. We have a question here and another question over there.
Thanks. Wonderful talk. Alex Ulfa, University of Agricultural Sciences. Do you think you could have detected more cases of mastitis or other health issues if you would have chosen the different temporal resolution of your GPS data? How often the sensor was recording the location? So the temporality of the question.
Yeah,
Thanks.
yeah, definitely yes, because it's a shame that the dispositive is only able to send a signal every 30 minutes. That I understand that it's because they want to have more battery because that dispositive along for a year, so it's quite good for this extensive production. But yeah, the 30-minute signals are really limited, limited a lot this, and probably all other CPUs like maybe 10 minutes or 15 minutes could be just better to have better results, but we should taste it. You know?
Short question. I've asked this before. Short question.
Okay. Mike Cassiano, University of Bern. Have you looked at all? You looked at activity, and you looked at the location. But have you looked at how repetitive the locations are over days? Do the animals go to the same locations? Does that vary? Did you say anything about that?
We didn't see that, but we are more interested in the pasture management. To maybe if actually through the mobile app you can see every day where there are the cattle. So maybe it would be interesting to find a kind of analysis that could advertise you if the cattle is still in the same place a lot of time, then have the possibility to move them. But there is not this kind of notification system yet, but it will be possible work it in the future.
Right, thank you very much. One of the technical team is pointing to me. There's a question online. Right, we will take an online question. We don't see it. We don't see it over here, I'm afraid. Right, here we go. So were there any differences in the body condition score between the two groups?
Sorry, could you repeat that?
Were there any differences in the body condition score? Did you pick up any body condition score effects? Do you think your location system might pick up an animal with a good condition versus a poor condition?
Okay, no, we didn't take, but maybe the next year we take about to see how the production affects, to have some indicators on how are the animals. But we check the animal first if they have already any illness or any problem to verify that it could happen before or during the grazing time.
Yeah. Great, thank you very much. It's good to see the technology being used in extensive systems. I think there's huge opportunities here. Yeah. And yeah, you've got some preliminary results, but really interesting results. So let's thank Roger once again.
Thank you very much.
Right, so the next speaker is going to be joining us, Humari. I'm hoping is Humari on Zoom, ready to give her presentation. Humari, can you hear me? Do you want to?
Yes.
You can, excellent. Sorry if I'm not pronouncing your name correctly. I can't give you the 2-minute warning, so you've got 12 minutes to talk, 3 minutes of questions. Over to you.
Okay. Is that okay?
Yes, that's good. We can hear you.
Thank you. Hello, everyone. My name is Homare Yamamoto from Osaka University, Japan. Today, I will discuss the humming of polar bear cubs and the changes observed during the developmental stages. First, let me provide some background to this study. Both white and captive polar bears give birth and rear their cubs in the maternity den for 4 months without eating or going outside. Generally, maternity dens are quiet and dark This picture shows the den used by our subject mother polar bear at the Tennoji Zoo. Caretakers at the Tennoji Zoo set up a camera in the den to monitor nursing behavior without interfering with the mother and the cub. In this study, nursing means breastfeeding. However, polar bear mothers often use their forelimbs to cover their cubs to keep them warm. As a result, it was difficult for the caretakers to observe the nursing behavior. Therefore, we decided to focus on humming. Well, what is humming? Humming is a loud vocalization characterized by sustained production over several minutes with very short interruptions. Most Earth Day calves produce humming. Previous studies reported that calves raised by mother bears produce humming during nursing. For example, in our observation of polar bears at the zoo, a female calf produced humming while holding her mother's nipple in her mouth. Now, I would like everyone to listen to a recorded humming. I will now play it.
Unfortunately, we can't hear that.
Oh, sorry.
Maybe you can hum like a polar bear.
Ah, okay. Like. That's okay. Thank you. Now that's.
Thank you. We know what it is, what it sounds like. Thank you.
Thank you. Thus, a short interval is interspersed between vocalizations that last for several seconds. A previous study reported that humming consists of a pulse and a pulse string. The pulse string is composed of pulses, and the pulse strings are divided by inhalation. What you have just listened to are the 3 pulse strings. It is also known that humming is continuously produced for several minutes, accompanied by pulse strains and inhalations. Therefore, we believe that repetition of pulse strains and inhalations may reflect nursing behavior. In this study, we define repetitions of pulse strains and inhalations as a series and regarded the series as an indicator of nursing behavior. Therefore, we consider that the frequency and interval of the series would approximate those of nurturing behavior. No studies have examined developmental changes in nursing behavior in Earth Day. Therefore, we aim to determine whether humming can be used as an indicator of developmental changes in nursing behavior. The methods used in this study were as follows. A polar bear mother and her female calf at the Tennoji Zoo were chosen as the subjects. The mother's name is Ich-chan, and the calf's name is Ho-chan. The calf was born on November 25, 2020. The study period lasted for 15 weeks after the calf's 1 week old, from December 3, 2020 to March 14, 2021. During this period, we set up a camera and recorded videos continuously. For the analysis, we sampled 24 hours of continuous videos twice a week. The total observation time was 720 hours. These images are the inside of the maternity den used by the subjects. A camera was installed on the ceiling near the entrance of the den, and the dimensions of the den were as shown in the images. Now, moving on to the analysis that we conducted. First, we performed a video analysis. We used instantaneous sampling every 34 minutes for 720 hours to check whether the mother and or the calf were visible in the video. The total number of sample points was 1,297 frames. Subsequently, we conducted two vocalization analyses. First, we investigated the structural characteristics of humming. We then investigated developmental changes in these structural characteristics. Continuous recordings of 720 hours were used, and 2092 series were recorded and analyzed. Now, let me move on to the results. This figure shows the number of frames where the mother and or the calf were visible. The main point is that there were no frames that captured nursing behavior. In other words, we could not capture the developmental stages in the nursing behavior of the calf through videos from the installed camera. Here, we observe the sound spectrogram of humming. The series was composed of continuous repetition of strains and inhalations. The series was separated by intervals of 0.4 seconds or longer. We analyzed the series that we consider to be more reflective of nursing behavior. We analyzed the developmental changes in humming from three different aspects: duration of the series, frequency per hour of the series, and interval duration of the series. The histogram shows the number of series durations separated by 10 seconds. Please look at the series shorter than 10 seconds. No previous study has reported the presence of such short humming, and the statistics, we found that the proportion was reduced at 2 and 3 months of age compared to 0 and 1 month of age. Regarding the frequency per hour and the interval duration of the series, the bar graph on the left shows that the frequency of series significantly decreased with age shown in months. The right bar graph showed that the interval duration of the series significantly increased with age. These figures show the developmental changes in humming. A decrease in the proportion of short duration series resulted in a decrease in frequency and an increase in interval time. In other words, as far as using humming as an indicator of nursing behavior, the results suggest that early postnatal nursing behavior in polar bears may decrease the proportion of short duration nursing behavior. However, do all series reflect nursing behavior? Short duration series, in particular shorter than 10 seconds, have not been reported in previous studies, and it seems to be difficult for calf to take mother's milk in a short duration of less than 10 seconds. These results suggest that the short duration series may not reflect nursing behavior. In all of the previous studies that observed polar bear humming, the calves were humming when nursing. However, one previous study that observed a captive sun bear mother and calves reported that the calves produced humming when the mother was licking the calves. It is possible that polar bear calves, as well as the sun bear calves, may produce humming when the mother is licking her calves. To summarize, we used a new and larger unit of humming, series. As a result, in this study, we reviewed developmental changes in humming for the first time. Previous studies have reported that calves raised by their mothers produce humming during nursing, and our observation that the female calf produced humming while holding her mother's nipple in her mouth suggests that the changes in humming may reflect developmental changes in nursing behavior. In addition, a short duration series was newly observed. However, it is difficult to assume that the calf was taking her mother's milk when she was producing a short duration series. In the future, we would like to resolve this problem by setting up multiple cameras in the den to observe the mother and the calves from various angles. By doing so, we believe that we can provide a method to monitor nursing behavior using the humming, even if the caretakers cannot observe the nursing behavior in the den. We are grateful for the kind support provided by the staff at the Tennoji Zoo. Thank you for your attention.
Right, thank you, Hamari. Very interesting, and thank you for doing your polar bear cub impression. Do we have any questions from the floor? We probably only have time for one question, which will be here.
Hello, Jasmine Music, McGill University. Thank you for your interesting presentation. I'm just wondering if you could explain maybe the reasoning or the function behind humming and why cubs will hum while nursing.
Yes, you mean the meaning of humming, right?
Yes, why do the cubs hum? What is the biological reason? Do we know?
Yes, thank you for your question. Previous studies suggest that humming indicates the cub's comfort or satisfaction, or that the cub promotes the emission of mother's milk. Does that answer your question?
Yes, I think it does. So thank you very much, Hamari. We need to move on.
Thank you.
Right, so we now have 10 poster presentations. So can all of the poster people, Xander, you're first, get yourself up here. Can all 10 of you please congregate round the back of the stage? I'm going to call you up in order. You have your 1 minute. To see you face to face. My co-author. This is my co-author. It's the first time I've seen him when he's not been on Zoom. So yes, if you can just come round, maybe around the back. Is that okay, Miro? We're not going to cause any technical issues. It's okay around there. Right, if we can. So I have my student helper here. So can you do the honors of doing the times? So you've got start, stop, reset. Right, so we're going to start with Xander.
PhD student at the University of Strathclyde in Glasgow, doing my research with a company called Peacock Technology Limited. Okay. My poster is about showing the generalization capacity of our cow identification model by evaluating it on an entirely new data set consisting of completely different cows that were used in training. So we show that our results are competitive with other methods that evaluate on the same cows as they use in training. So if you're interested in AI, and that is artificial intelligence, not artificial insemination, I know next to nothing about the latter, so please don't ask me any questions on that. Then come see me in the poster session later.
Right, thank you very much. Next up, we have a very shy young gentleman, Miro, so please.
Yeah, hi, my name is Miro. My poster is about how to organize an ISAE conference. No, that was different thing. No, in meantime, we actually, what we've done, we use boluses we put in cows in the rumen. This reticular ruminal, we measure a reticular ruminal temperature. So we measure the temperature inside the rumen in order to identify the period of water intake. So how can we use this for determining the number of water bouts and what is the behavior behind that? In order to use for that, we use different seasons. Once in September we measured, and once we measured in January. The temperature was quite a little bit different between, of course, in Macedonia it is between summer and winter. But what we found, we didn't. If we use a threshold, if we use a threshold with what we measured below one's temperature of below 1 Celsius, then we couldn't find any differences of the drinking behavior.
Don't talk to me about his poster.
Or tonight.
Right, next up we have Emily.
Okay. My name is Emily Rice. I work at the University of Kentucky. What we looked at for this research was determining if there's an association between technology recorded behaviors with calves, pre-weaning calves, and heat stress, so like elevated temperature, humidity in the environment. So what we saw was that there was increased restless behaviors, as well as other things, but for the sake of keeping things short. My poster is number 42, and I'd love to talk about heat stress.
Right, thank you very much. Well within time, Emily. An interesting poster. So, Ina, you're next.
Hi, my name is Anna Dobrik, and I'm from the Faculty of Veterinary Medicine in Skopje. So we had actually a concept for future research that we wanted to present it to you in form of a poster. The name of the poster is Developing Models from an Optimized Number of Sensors Used for the Welfare Assessment of Dairy Calves. So the idea is to use the most versatile or multifunctional sensors that are used in precision livestock farming to be able to continuously acquire data real time about the welfare of the animals on the farm. And the idea is, and this will be done by measuring the welfare criteria in the welfare quality protocol for dairy cows. The idea is the goal is for the farmer manager, the stakeholders, the veterinarians to continuously have information about the welfare of the dairy cows on the farm. If you're interested to hear more about this, come to my poster session in poster room 1. My number is 43. Thank you for your time.
Perfect. That was pretty much bang on a minute. So I think Aidan, you're next up.
Hello, my name is Aidan, and my poster is on a review of studies evaluating clinical illness scoring for detecting bovine respiratory disease in cattle in preparation for another study to work on developing a new clinical illness scoring system. What I found was that there are a lot of differences between what signs are used in beef cattle and dairy cattle. And most substantially, one of the behavioral signs that's commonly used, referred to as depression or lethargy, was used in all studies of beef cattle, but it only had any kind of operational definition or scoring system in one study. So that's something that I want to be careful to include in the future. And my poster is in the front of poster room 1.
Right, thank you very much. That was bang on time, Aidan. Next we have Lewis. You're up, please.
Hi, hello everyone. So my name is Luis Garrido. I'm a PhD student at the Catholic University of Paraná. And my research area is precision livestock farming. So throughout the years, many precision livestock farming technologies were developed to detect respiratory diseases. However, we were wondering, do they work? So we did a systematic review, and an overview of the results is that we're still not there yet, but there's much more to discuss. So please come to poster 45 so we can talk about it. Thank you.
Fantastic. Nice, well on time presentation. Barbara, you're up next.
Hello, everyone. My name is Barbara Bagiova, and I'm from the Slovak Academy of Sciences, and I'm a PhD student. Our poster is number 46, and it's about use of accelerometers for automated monitoring of lane hands behavior. And it was a pilot study, and we tested if the dictionaries made by Abdali about behaviors are consistent with our annotated data of these enhance behavior, but we found that it was inconsistent. And that there is further work needed to improve the algorithms, and we collaborated with faculty of mathematics and informatics because we can't do those mathematic things, of course. So.
And your poster 46. Thank you very much, Barbara. So, Stefania, you're up next.
Morning, I'm Stefania Cerozzi from the University of Milan, Italy, PhD student. The poster I'm presenting focuses on the preliminary results of the CAPRA project that wants to examine in depth the acoustic communication in the dog species thanks to the application of bioacoustic technique. In fact, a greater understanding of dog signals by humans will help improve the quality of the human-animal relationship, but also the welfare of dogs, thanks to an early intervention in farming development. With this in mind, we look for the distinctive characteristics of organizations emitted by goats in different contexts. These preliminary results will allow us to evaluate the possibility to implement an IT for farmers in order to monitor those vocalizations and merits.
Right, thank you very much, Stefania. I think Nina, you're the last of our in-person presentations. Over to you.
Yes. Hi, my name is Nina and I come from the Norwegian University of Science and Technology. My poster is the result of my master thesis where I studied the movement pattern of sheep while on rangeland pastures. And I used high density GPS collar data from about 400 sheep over the course of 8 years while on pasture to determine their data-driven description of their behavior while on rangeland pasture. And I did this using the unsupervised machine learning models, k-means and dbScan. And diurnal behavior could be identified. The model categorized their behavior into 4 characteristic behavior periods, which is visualized on the screen here. And also from the outliers of the behavior, I could identify atypical movement, which could be used as threshold values for when the herd
This is sweetie.